Hello, Honors Chemistry. This is your second video. We're going to be dealing with the gas laws and the combined gas laws. I'm going to be referring to your notes. This is slide number 15. I'm going to be referring to slide number 19. This is slide number 19. And I'm going to be referring to slide number 18, I believe. Not in that order. That's slide number 18. So here we go with a quick review. Yesterday's video we learned about Boyle's law, Charles' law, and Gay-Lussac's law. Together they're called the gas laws. Boyle's law relates the pressure of a gas and the volume of a gas. Let's say we have a balloon. The pressure of a gas and its volume in the balloon are related inversely proportionately. So as the pressure climbs on the outside of that balloon, let's say if we were to increase the pressure on the outside of the balloon, so here's your balloon, the volume, if the pressure goes up, the volume goes down. If we were to double the pressure, we would halve the volume. Because it works that way, whenever we multiply these two together, we'll get a constant. Now we rarely care about what that constant is. What we often care about is beginning conditions signified by the number 1 and ending conditions signified by the numbers 2. So my beginning pressure on the balloon and my ending pressure on the balloon, my beginning volume on the balloon, and then what is the new volume after the pressure change. They're inversely related. The other two gas laws are directly related. That means as one goes up, the other goes up. Charles' law, as the Kelvin temperature doubles, the volume of the gas will double. So if you took a balloon and you were to heat it up and double the Kelvin temperature, you'll double the size of the balloon. So no matter what you do to these two numbers, you'll get a constant. Again, we rarely worry about what the constant is. What we care about is beginning conditions and ending conditions. So if I had a balloon and I warmed it up, how much bigger would it get? If I know 3 of the variables, I can solve using algebra for the 4th. And Gay-Lussac's law is also a direct relationship. As you take the pressure of a trapped gas divided by its Kelvin temperature, you will get a constant. In this case, your container has to be unable to expand. Let's say like an aerosol can. I'll explain why in a minute. If I were to double the Kelvin temperature on that aerosol can, the pressure inside would double. That's a direct proportion. And for the same reasons as I mentioned above, we don't care about what the constant is. What we care about is beginning conditions and ending conditions. Now for all of these laws to work, we need to refer back to the slide number 15. The green one, Boyle's law. For it to work, the other two variables must remain constant. So because Boyle's law relates pressure and volume, that's this one, the temperature of the gas and the number of moles of gas have to remain constant. Let's go back to this example. As I change the pressure on the balloon, I can't warm it or cool it, and I can't have a leak in the balloon or be blowing up the balloon during this experiment. For the green relationship to be true, temperature on that balloon and the number of moles of gas in the balloon must remain constant. Now Charles' law is the blue one here. In order for that to be true, the pressure on the balloon has to be constant, and the number of moles of gas, so this N is moles of gas, in the balloon can't change during the experiment. For Gay-Lussac's law, which is the red one, to be true, the volume of the container, remember I said I'd refer back, an aerosol container that's made out of steel can't expand or contract. The volume must remain constant, and there can't be a leak in the container for Gay-Lussac's law to be true. Now, that's a lot to remember, but we can actually make it easier because we can put all 3 of these laws together in what's called the combined gas law. The combined gas law is exactly what you would think it is. It is the 3 laws combined. If I hold temperature present, that is Boyle's law. If I hold temperature constant, that is Boyle's law. If I take out the P's, that's Charles' law. If I take out the V's, that's Gay-Lussac's law. So they're all 3 here, but what's nice now is all 3, the pressure, volume, and temperature can change at the same time, as long as I don't have a leak in the system, as more moles of gas aren't getting out or coming in, the combined gas law will always work. So let's actually use an example. We're going to use slide 18 first. I call it the tire question. It's this question in your notes, and I'll draw a picture of what's going on in this question. So you have a tire, let's say, on your car. I'll make a bad picture. And we want to know the new volume of a tire. So I'll draw two tires. So this is going to be the original, and then this will be the ending. Now I drew it bigger. I don't know if it's going to get bigger or smaller. What is a new volume? So I want to know V2, the new volume. If it originally had a volume of 35.1 liters at 745 millimeters of mercury, that's a pressure, and 21 degrees Celsius, and then was changed to 765 millimeters of mercury and 29 degrees Celsius. So these are my pressures, and this is my beginning volume. I want to know my ending volume, and then my temperatures change like that. Well, this was made for the combined gas law. P1 V1 over T1 equals P2 V2 over T2. This is what we call in science plug and chug. We're going to plug the numbers in where they belong and solve for V2. We want to know the new volume of the tire. Now what's my beginning pressure? So these are the ones, and then these are the twos. My beginning pressure is 745 millimeters of mercury. What's my beginning volume? That was 35.1 liters. And then what's my beginning temperature? Well, that was 21, but you have to remember that we have to add 273. For all the gas laws, the temperatures have to be in Kelvin. They will not work in Celsius, because we need an absolute temperature scale, one that has a true zero. If you remember, Kelvin can be found by taking degrees Celsius and adding 273. That's what I did here, took degrees Celsius and added 273. Now, if I do my math real quick, that's for 294 Kelvin. Now, so I know what this side is, P1 V1 over T1. What's my ending pressure? Well, that's 765 millimeters of mercury. It's right there. And I want to know my ending volume, V2, at 29 degrees Celsius. My second temperature is 29, so I'm going to do 29 plus 273. Now, if I added 30, no, let's just add, so 273 and 29 is 12, so 302. If I did the math right, and it looks good. So now all I have to do is the algebra to solve for V2. So what would I do on my calculator? I'm going to solve for this whole side. So I'm going to take 745 times 35.1 and divide it by my 294. So this side is about 89. Now, because we're dividing by 302, to move it, I'm going to multiply by 302. And because I'm multiplying by 765, I'm going to divide by 765. Again, I'm swinging everything onto this side so I see what V2 equals. And I get a volume of 35.1 liters. Now, at first this seems very discouraging because that's what I started with for the volume of my tire. It didn't change. But let's look why. Why didn't it change? Well, if I drew a picture of the tire, another picture of the tire, let me do it in black. So here's our car tire. It got colder. No, I'm sorry, it got warmer. 8 degrees warmer. When it gets warmer, that would make it want to expand. But the pressure on the outside, the external pressure, increased. So it was 745 and it went up. It got bigger. Well, a bigger pressure on the outside would tend to make the tire want to shrink. And what ended up happening is I negated my temperature increase, negated my pressure increase, and the tire stayed the same size. So that's our first example of using the combined gas law. I have one more for you here, and that's going to be slide 19 in your notes, and your notes are found in Schoology. maybe something more exciting will happen here. I call it the bubble question. Slide number 19 looks like this. And I'll go ahead and draw a picture of the situation we have. We have a bubble. So this is the first bubble. Well, it's the same bubble, but we want to know, is it going to get bigger or smaller? I'm going to draw it as if it's bigger. I really don't know if it's going to get bigger or smaller. It's the same bubble, the same trapped air mass. Remember, N has to stay the same. It can't leak air or gain air. So the child blows a bubble at 28 degrees Celsius and has a volume of 23 centimeters cubed. Now, that's the same thing as a milliliter at 1 atmosphere of pressure. Those are the beginning conditions for the balloon. As the bubble rises in the atmosphere, it encounters a pocket of cold air, which is only 18 degrees Celsius. So our temperature drops 10 degrees Celsius. If there's no change in pressure, so pressure is going to stay at 1 atmosphere, what is the new volume of the bubble? Again, I want to know V2. So let me go ahead and write the combined gas law. One reason you know you're going to use the combined gas law is you will have 5 unknowns. And notice we have 1, 2, 3, 4, and 5. Or 5 knowns and 1 unknown, I should say. So I'm looking for V2. What's my beginning pressure? Well, notice the pressure didn't change. And we have 2 options. We can just get rid of pressure, which is probably the better option. I'm just going to get rid of pressure. No matter what the pressure is, if it stays the same, it's going to cancel out of the equation. Now notice if pressure remains constant, this is Charles' law. And so we're really just using Charles' law. So anytime it says something remains constant, you can take it out of the combined gas law. What's my beginning volume? Well, that bubble was 23 centimeters cubed. What's my beginning temperature? Well, 28. 28 plus 273. Now we have to have that in Kelvin. What's my ending volume? That's what I'd like to know. Did the balloon get bigger or smaller? And my ending temperature is 18. Now we should know whether it got bigger or smaller. It got colder. Because it got colder, it actually should have shrank. So I should have drawn it smaller. So it should be smaller than 23. Well, let's do the math. Let me solve these. 273 and 28. If I did my math right, that's 311. You check it real quick. Oop. It's 301. I thought it didn't look right. 301. And then 273 and 18. 291. Yep, makes sense. So, how would I do the algebra? I'm going to solve this side by taking 23 and dividing it by 301. And I'm going to multiply to pull it over by 291. And the balloon shrank to 22.2 centimeters cubed. We could also call that a milliliter. So it went from 23 to 22.2. You might think that didn't shrink very much. But as a percentage, the Kelvin temperature didn't change that much. If the Kelvin temperature were to halve, it would have to be 150 instead of 300, for example. So it didn't change that much. In Kelvin, as a percentage of 300, it didn't change very much. That's why the volume didn't change very much. So what did we do today? We did 2 combined gas law problems. Slide 18 and slide 19. And then we reviewed the individual gas laws. And the individual gas laws were Boyle's, Charles, and Gay-Lussac's. You don't have to be able to use them individually if you can use the combined gas law. Hope you have a good day today, Biden. Bye-bye.